Today we're doing a deep dive into an overview by Abhinay Anand, really pulling out the crucial bits about this oceanic crust.
Yeah, think of this as, a quicker way to get your head around a really key piece of the Earth puzzle. Our mission, really, is to explore this crust, how thick it is, or rather, how thin, what it's made of, its age, how it forms.
Its thickness. The source says it averages just 6 to 7 kilometers.
Yeah.
That's only 3 to 4 miles. What really strikes me is how incredibly thin that is compared to the continents we live in.
Thin. Yeah. Continental crust can be, well, tens of kilometers thick,
Wow.
easily. So this difference, this relative thinness of the oceanic crust, it has huge consequences. And like the source mentions, it's not perfectly uniform either. You get local variations.
Oh, right. Depending on melting below and how fast the plates are moving apart.
Exactly how much melt comes up from the mantle, how fast those mid-ocean ridges are spreading. It all affects the thickness right there. So it's a dynamic thing right from the start.
Okay, composition. This is where, for me, it gets really interesting. The document says it's mainly magnific rocks, rich in magnesium and iron. They even use the term silica magnesium, I guess.
Yeah, it's a handy shorthand. Heavy stuff.
And the star player seems to be basalt. Often as these amazing pillow lavas near the top, I just picture these round, bulbous shapes forming as hot lava hits that cold seawater.
You got it. Those pillows are like instant visual proof of underwater eruptions. And then just beneath those pillows, you find what are called sheeted dikes.
Okay.
Picture vertical walls of basalt that solidify. They were basically the plumbing system, feeding the lava upwards to form those pillows.
Ah, okay, the feeders.
Right. And then deeper still, the lowest layer, you get gabbroic rocks. Now, gabbro, it's basically the same stuff as basalt, chemically, but it cooled much more slowly, deeper down.
Like the difference between cookies baked quick and a cake baked slow.
Kind of, yeah. Same ingredients, different cooling time gives you a different texture, larger crystals in the gabbro that had time to grow them.
Okay, that makes sense. So the main minerals listed are olivine, pyroxene, plagioclase feldspar, and these iron titanium oxides. Sounds quite different from granite and continental rocks.
Totally different mineral suite. And connecting this to the bigger picture, the source notes something important. Oceanic crust is depleted in certain elements.
Depleted, like missing them.
Well, less of them compared to continental crust. Things like rubidium, uranium, potassium, some rare earths. This tells us something about where the magma comes from. It suggests the mantle source for oceanic crust has, already lost some of these elements over Earth history. It's like a chemical fingerprint.
Interesting. Okay, let's shift to density. This seems absolutely critical. Oceanic crust is denser than continental crust, average around 3.0 grams per cubic centimeter. Yeah. And that comes down to all that iron and magnesium, right? Heavier elements.
Exactly right. More mass packed into the same volume. And this isn't just like a fun fact. It drives one of the biggest processes on Earth.
Subduction.
You got it. The source points this out clearly. Because it's denser, when an oceanic plate collides with a continental plate, the oceanic one always loses. It sinks or subducts down beneath the lighter continental plate back into the mantle.
Wow. And that creates ocean trenches and volcanoes on the continent.
That's the engine behind them, yeah.
This one really surprised me in the reading. The oldest oceanic crest is only about, 180 to 200 million years old? Western Pacific, Northwest Atlantic.
Yeah, which sounds ancient to us humans, but geologically,
It's nothing.
practically brand new. Continental rocks can be billions of years old, billions with a B.
So why is the ocean floor so young?
It's this constant cycle. Birth and death, essentially. New crust is always being made at mid-ocean ridges, and the old crust is constantly being destroyed, recycled back into the mantle at those subduction zones.
Ah, okay. So it doesn't get a chance to get really old.
Exactly. The average age, the source says, is around 60 million years, which just highlights this, constant conveyor belt. The ocean floor is always being refreshed.
Okay, so let's zoom in on that creation process. It all happens at mid-ocean ridges.
Right. Divergent plate boundaries, places where tectonic plates are literally pulling apart.
Like the Earth is unzipping itself underwater.
That's a great way to put it. As the plates separate, magma from the mantle rises to fill the gap. It erupts as lava, hits the cold water, cools super fast, making those pillow basalts we mentioned, and solidifies. New crust.
Seafloor spreading.
That's it.
Yeah.
And as more magma comes up, it pushes the older, newly formed crust sideways, away from the ridge, like a slow-motion conveyor belt, constantly adding new material in the middle.
And the evidence for this? The document mentions magnetic stripes. This is brilliant. Can you unpack that a bit? Why are they so important?
Oh, absolutely. This is like the smoking gun for seafloor spreading. As that lava cools and solidifies into rock at the ridge, tiny magnetic minerals inside it, mostly iron oxides, they act like little compass needles. They align themselves with whatever direction Earth's magnetic field is pointing at that moment in time.
Okay.
But here's the cool part. Earth's magnetic field flips. North becomes south, south becomes north periodically. It's called a magnetic reversal.
Right, I've heard of that.
So as new crust forms and spreads away from the ridge over millions of years, it records these flips. The kinds of waves generated by earthquakes, or that scientists use deliberately to probe the Earth.
But they travel at different speeds depending on what they're going through.
Exactly. P waves are compressional, faster. S waves are shear waves, slower, and they can't travel through liquid. Their speeds change based on the density and stiffness of the rock or sediment. The document gives ranges. T waves in solid oceanic crust are 3.5 to 7.2 kilometers slower in loose sediment. S waves may be 1.8 to 4.2 kilometers in rock.
And it contrasts that with continental crust speeds, which seem generally a bit different, maybe slightly higher on average for P waves.
Yeah, the exact speeds depend on the specific rock type, temperature, pressure.
Perfect transition.
Yeah.
So the layering, it's not just one solid block. Layer 1 is on top.
Right, the sediment layer. Pretty thin, average maybe 0.4 kilometers.
And it's thinnest near the ridges where the crust is brand new.
Makes sense, yeah.
And gets thicker further away as more stuff rains down over time.
Exactly. And that stuff, layer 1, it's a mix. You get pelagic sediments, the microscopic shells and skeletons of marine organisms sinking down.
Okay.
Terrigenous sediments, which is basically dust and clay washed or blown off the continents.
Land-derived stuff?
Right. And volcanic ash from eruptions settling down too. So it's a record of ocean life, climate, and volcanism.
Cool. Then below that, layer 2, which is split. 2A and 2B.
Yeah. Layer 2A is the uppermost volcanic part, about half a kilometer thick. That's where you find those pillow basalts, glassy or very finely crystalline basalt, the stuff that erupted right onto the seafloor.
Okay, the surface lavas.
Then layer 2B below that is about 1.5 kilometers thick. This is mainly those sheeted dikes we talked about.
The vertical plumbing.
Vertical plumbing, exactly. The conduits that fed the lavas of layer 2A.
Got it. And finally, the biggest layer, layer 3.
Yep, layer 3. This is the bulk of the oceanic crust, about 5 kilometers thick. This is where you find the gabbro, that coarse-grained, slowly cooled equivalent of basalt. And sometimes, right at the base, you even get cumulate ultramorphic rocks, like peridotite, which are residues from the magma chamber, even denser stuff.
So this formed deeper down, cooling much more slowly in a magma chamber beneath the ridge.
Precisely. That slow cooling allowed those larger crystals to grow. So while the pillows and dikes are maybe more, visually dramatic representations of the volcanic action, layer 3 is the real foundation, making up most of the volume.
So putting it all together, oceanic crust,